Hello everyone, today we're going to be learning about rational functions. Rational functions is a quotient of polynomial functions with the form of f of x equals n of x being the numerator divided by d of x being the denominator. In general, the domain of a rational function of x includes all real numbers except x values that makes the denominator 0. That's why here appears d of x different from 0. And much of the focus will be on the behavior of the graph near these excluded x values. Let's see this with an example. In this case, we have f of x equals 1 divided by x. The denominator is 0 when x is equal to 0. So the domain of f is all real numbers except x equals 0. To determine the behavior of f near this excluded value, we are going to evaluate f of x to the left and to the right of x equals 0. So we are going to use intervals like powers of 10 close to 0, as we can see in here. And now if you're asking why did I choose a minus 0.5 in here, well, this minus 0.5 is like a middle step. It's not too close to 0, but it's close enough. So this helps us to see the function increasing in magnitude. If we only use the powers of 10 values, the graph looks like it suddenly jumps to negative infinity. We're going to be using these notations over here. This means that x approaches 0 from the left, and this means that f of x decreases without bound. That's what we got from the evaluation of our numbers. Now, if we want to say that x approaches 0 from the right, that is the opposite, this is what we are going to use. And if we want to say that f of x increases without bound, this is what we are going to use. In conclusion, as x approaches 0 from the left, f of x decreases without bound. In contrast, as x approaches 0 from the right, f of x increases without bound. We can express this with this notation over here, and we are saying exactly the same. Let's introduce a new concept, vertical and horizontal asymptotes. By definition, we have the line x equals a is a vertical asymptote of the graph f when f of x increases or decreases without bound as x approaches a either from the right or from the left. And we also have the number 2 that says the line y equals b is a horizontal asymptote of the graph of f when f of x approaches b as x increases or decreases without bounds. Eventually, as this happens, the distance between the horizontal asymptote and the point of the graph must approach 0. Following these definitions, in the previous example, we have that the line x equals 0 is a vertical asymptote of the graph of f, and we also have a horizontal asymptote that is the line y equals 0. This means that f of x approaches 0 as x increases or decreases without bound. As we defined a rational function before, now we are going to define the numerator as a sub n times x to the power of n plus a sub n minus 1 times x to the power of n minus 1 plus a sub 1 x plus a sub 0. And let's define the denominator by b sub m times x to the power of m plus b sub m minus 1 times x to the power of m minus 1 plus b sub 1 times x plus b sub 0, where the numerator and denominator have no common factor. How we find these vertical and horizontal asymptotes? The graph of f has a vertical asymptotes at the zeros of the denominator. The graph of f has at most one horizontal asymptotes determined by comparing the degrees of the numerator and denominator. What happens now if the degree of the numerator is less than the degree of the denominator? The graph of f has the line y equals 0, that is the x-axis, at the horizontal asymptote. What happens if the degrees are equal? Well, the graph of f has the line y equal a sub n divided by b sub m as a horizontal asymptote, where a sub n is the leading coefficient of the numerator, and b sub m is the leading coefficient of the denominator. What happens if the degree of n, the numerator, is greater than the degree of the denominator? In this case, the graph of f has no horizontal asymptotes. Let's try to find all vertical and horizontal asymptotes of the graph of this rational function that we have over here. So let's follow these steps that we talked before. So to find the vertical asymptotes, we need to set the denominator equal 0 over here. Then what we're going to do is to factor. Then we are going to set the first factor equal to 0 and the second factor equal to 0, and we are going to have x equals minus 1 and x equals 1. These are the vertical asymptotes. Now let's find the horizontal asymptotes. We have the numerator with degree 2 and the denominator with degree 2. So n is equal m. So the graph of f has a line y equals a sub n divided by b sub m that are the leading coefficients of the numerator and the denominator. So in this case, we have leading coefficient 2 in the numerator and leading coefficient 1 in the denominator. So we are going to have y equals 2 divided by 1, that is equals 2. This is our horizontal asymptote. Let's try to sketch the graph of this rational function. The first step is going to be simplify the function if possible. In this case, we already did it. The second step is to find and plot the y-intercepts by evaluating the function 0. So in this case, we have 0, 0, or y-intercept. The third step is to find the zeros of the numerator. This is the x-intercepts. So we need to set the numerator to 0, and this is 0, 0 in this case. The fourth step is to find the zeros of the denominator, and this is the vertical asymptotes. We already did it, and we have the lines x equals 1 minus 1 and x equals 1. The fifth step is to find the horizontal asymptotes. In this case, we have y equals 2. We already did it before. And the step number 6 is to plot at least one point between and one point beyond each x-intercept and vertical asymptote. So this is what we need to do. Let's use these intervals using the test intervals that we learned before in other chapters. In this case, we have negative infinity minus 1 with a representative x value that I choose minus 2. So we evaluate minus 2 in the function, and it's 2.67 with a positive sign, and the point in the graph is going to be minus 2, 2.67. The same with the interval minus 1, 1. The representative x value is going to be 0.5. We evaluate 0.5 and we have negative 0.67 with a negative sign, and so this is going to be our point in the graph. And the last interval is going to be 1, infinity. The representative x value is going to be 2, and we evaluate 2 in the function, and we are going to have 2.67 with a positive sign, and the point in the graph is going to be 2.67. The step number 7 and the last one is going to be to add all these values, all these steps in the graph. And so here we can see the points, 2.67, negative 2.67, we have the point 0, 0, the point 0.5, negative 0.67, and of course we need to represent the horizontal asymptote and the vertical asymptotes. And this is our final result. Our last topic of the class is slant asymptotes. The degree of the numerator is exactly one more than the degree of the denominator. In the example that we have here, f of x is equal x to the power of 2 minus x divided by x plus 1. The degree of the numerator is equals 2 and the degree of the denominator is equals 1. Using long division to divide x plus 1 into x to the power of 2 minus x, we have f of x equals x minus 2 plus 2 divided by x plus 1. This x minus 2 is our slant asymptote. As x increases or decreases without bound, the remainder 2 divided by x plus 1 approaches 0, so the graph of f approaches the line y equals x minus 2. And here we have the graph. The slant asymptote is a green line, y equals x minus 2. And this is all for the class.